Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called Oil and Gas Industries Enterprise-Wide Optimization, Oil and Gas State Estimation, Oil and Gas Production. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. The image shows the chain of petroleum products. This video discusses use cases of the Kalman filter at the top of the chain, crude oil and gas production. Rudolf, Rudy, Emil Kalman was a Hungarian-born American electrical engineer, mathematician, and inventor. Rudolf Kalman was born in Budapest in 1930. After emigrating to the United States in 1943, he earned his bachelor's degree in 1953 and his master's degree in 1954, both from the Massachusetts Institute of Technology. Kalman completed his doctorate in 1957 at Columbia University in New York City. Kalman was most noted for his co-invention and development of the Kalman filter, a mathematical algorithm that is widely used in signal processing, control systems, and guidance, navigation and control. For this work, U.S. President Barack Obama awarded Kalman the National Medal of Science on October 7, 2009. In statistics and control theory, Kalman filtering, also known as linear quadratic estimation, is an algorithm that uses a series of measurements observed over time, containing statistical noise, and other inaccuracies, and produces estimates of unknown variables that tend to be more accurate than those based on a single measurement alone, by estimating a joint probability distribution over the variables for each time frame. Kalman filter applications in oil and gas production. Case: oil gas lifted wells. This section is based on the paper State Estimation of Gas Lifted Oil Well Using Nonlinear Filters. The artificial lift methods are beam pump, hydraulic pump, PC pump, gas lift, and ESPs. Gas-lifted systems are usually situated in harsh environments, or deep below the sea surface, for sensors to produce reliable measurements. This is due to the difficulty encountered when deploying the sensors in the location required, to provide good measurement, excess heat effect on the sensors, and reaction between the sensors and the harsh environments, among other reasons. Most control solutions in gas-lifted systems rely on these sensor measurements, hence the states or variables used in the controllers are unreliable. Exist experiences in where a control solution was used to eliminate casing heading instability, assuming all measurements were available and reliable. However, it is possible to use topside measurements and Kalman filter to estimate the states for the controller. The performances of the state methodologies on gas-lifted systems vary, due to the dependence of the model on the underlying assumptions used at the modeling stage, in addition to the noise probabilistic hypothesis. In the linear case, the Kalman filter is the optimal estimation method. But a gas-lifted system is inherently nonlinear, and nonlinear filters such as the extended Kalman filter, EKF, unscented Kalman filter, UKF, or particle filter, PF, among other nonlinear state estimation methods, should be used. The article presents the application of EKF, UKF, and PF to gas-lifted systems, and examines their performances, examining the residuals and performing hypothesis tests on the residuals. The gas-lifted system is one of the artificial lift methods employed when the natural energy for lifting hydrocarbons, from the reservoir into the production platforms, becomes insufficient. The input is the percentage valve opening, that controls the flow rate of produced fluid through the production choke. In other cases, the flow rate of lift gas into the annulus is also considered as input, but here the authors fix it with a regulatory controller. The measurements are annulus pressure, PA, wellhead pressure, PWH, and mixture density, RT, which are readily available from the sensors and are reliable. Figure is a schematic of a gas-lifted system. The states are the mass of gas in the annulus, the mass of gas in tubing, and the mass of oil in tubing, indicated as X1, X2, and X3 respectively. A gas-lifted system sometimes goes to a depth of several hundreds of meters below sea level, making it difficult for sensors to provide accurate measurements of the states. The key features of the system are the two volumes, which are the annulus, that holds X1, and tubing, that holds X2 and X3. The reservoir pressure, PR, provides the natural energy for lifting the crude up to the storage tank. Lift gas enters through the gas lift valve, and out through the production choke, while the injection valve connects the annulus and the tubing. All variables in a gas-lifted system are positive. The gas-lifted Kalman model focuses on the formulation of the equation of state variables, which is summarized in a system of finite differences that explains the dynamic evolution of the system. The table shows the state variables included in the model, for each of which the modeler must formulate an equation. All of them are considered random variables, which must be characterized probabilistically, starting from the first two moments of their multivariate distribution function. The equations include the algebraic formulation, and the parameters of that formulation. The uncertainty in the state variables derives from these two aspects. The equations that represent the dynamics may be imperfect, and/or. The parameters included in the equations can be known imperfectly, making them random variables. The modeler must decide whether the parameters will be handled as deterministic, or if they will be handled as random variables, and therefore included in the process of state estimation. The table shows the parameters included in the gas-lifted Kalman model. Below are the equations that are part of the dynamical model, that describes the behavior of the system. The mass differential equations are presented in the image. The flow rate equations are presented in the image. The pressure equations are presented in the image. The density equations are presented in the image. Figure shows true and estimated states of gas-lifted systems using the extended Kalman filter, EKF. All three states estimates, red dotted lines, converge to the true states, blue solid line, about the same time. These states are the mass of gas in annulus, the mass of gas in tubing, and the mass of oil in tubing, respectively. True and estimated states of gas-lifted systems using the unscented Kalman filter, UKF. The estimated states converge at different times, with X2 being the fastest, and X3 slowest. Estimated states full residuals of gas-lifted system using EKF, UKF and PF. The residuals from estimating using PF is the poorest for the three measurements. The UKF has a smaller residual than the EKF for PA and PWH but bigger for RT, indicating that the UKF still has the best estimation performance, by residual visualization. Standardized errors are obtained by dividing each error by the corresponding steady-state value. Case: modeling oil and gas flows in well fields. This section is based on the paper Modeling Fluid Flows in Oil Fields Using the Kalman Filter. The paper presents a statistical model of the relationship between injection and production wells on an oil field. The model is based on the analysis of the fluid flows that occur in the oil field. Its modeling is oriented to a Kalman filter model. In this case, there is no direct physical model based on differential equations. Therefore, the modeler must create an algebraic model, which serves as the basis for an equivalent probabilistic model, whose parameters can be estimated through the Kalman filter. In oilfield development, the reservoir flooding method is widely used. Water is pumped into a reservoir through injection wells, which displace the oil from the reservoir, thus increasing oil production in the producing wells. However, the complex internal structure of the reservoirs, and the configuration and position in space, complicate the process of constructing an accurate mathematical model. Currently, there are several models that describe fluid flow processes in a reservoir. Some are based on differential fluid flow equations, filtration models, that adequately describe the internal structure of a reservoir, but the effectiveness of the model is only achieved with a high cost of calculation, and Kalman filter provides stochastic models that produce satisfactory approximations, with lower computational costs. One of the interests of the oilfield developers is to establish the efficiency of the operation of certain injection wells, to establish an effective flooding of the reservoir. With filtration models, it is difficult to establish response functions about the impact of certain injection wells on specific production wells. Through the Kalman filter, statistical and calculation problems are modeled in such a way that it is easy to find a relationship between the performance of injection wells and production wells. Statement of the problem. We denote the sets of production and injection wells by L and M, respectively, then Q, equal to L united with M, is the set of all wells, for which their perforation Cartesian coordinates xm, including depth of the perforation, are known. For each production well, the production history of oil VZMT, and water VWMT, is known, where the T index indicates the periods in which the operations were carried out. In addition, the duration of well operation, PMT, is known. If the well is idle at time t, these values are equal to 0. The production history is divided into production history averaged over the months, and number of hours of operation per month. Mathematical model. Modeling the processes that occur in a reservoir according to the accepted approach in filtration theory, FT, we divide the reservoir into sufficiently small fragments and construct their dynamics. The division of a reservoir is represented in the form of a graph. Each vertex in the graph corresponds to a certain domain of equal size within the reservoir. Subsequently, we assign to each vertex the amount of fluid in the domain, oil, and water. The edges of the graph correspond to the flows of water and oil in the reservoir. N is the ordered set of vertices, and N is the set of neighboring vertices for the nth vertex. Let xn be the coordinates of the nth vertex in the coordinate system D, and D a metric in the set D. Graph, with vertices indicated by circles, with hexagonal environments in the coordinate plane, associated with the geographical coordinates of the wells. Production wells are indicated by squares. Numbers mean the indices of the vertices of the graph, and the indices of the wells. The edges of the graph are marked with solid lines. The dotted lines indicate the set SOM. That describes the topology of the network. The edges of the graph correspond to the flows of water and oil in the reservoir. N is the ordered set of vertices, and N is the set of neighboring vertices for the nth vertex. Let xn be the coordinates of the nth vertex in the coordinate system D, and D let be a metric in the set D. Let SOM is the set of the vertices closest to M with respect to the metric D. For SOM, the magnitudes of the influence of the vertices are defined in the equation 1. This definition guarantees that summation on n of the weighting factor, QMN, is equal to 1. For a vertex n, HWNT represents the amount of water at time t, and HCNT the amount of oil. Fluids flow between adjacent vertices are linearly proportional to the difference between the fluid levels at the vertices. The coefficients of proportionality between the vertices K and N are equal to theta Z naught, and theta W naught for oil and water, respectively. Each injection well increases the amount of water at N vertex by QLN times ULT, an amount multiplied by time. Oil and water exit through the production wells. The amount of oil outgoing is presented in equation 2, while the amount of water outgoing is presented in equation 3. Eta Zm and eta Wm are unknown parameters. Given the uncertainty in the parameters, for each vertex the white noise epsilon r and t, where r is equal to z, oil, or w, water, assuming a normal distribution with means 0, and unknown variance sigma r, h square. Additional information SMT may be included in the state equation for fluids exiting the N vertex. The equation 4 define the amount of oil tons, and the equation 5, the amount of water tons. ZZM and ZWM are unknown parameters. Thus, the dynamics of the amount of fluid at the vertex N is governed by the following stochastic equations. Thus, the dynamics of the amount of fluid at the vertex N is governed by the following stochastic equations. Introducing the equation 6. Where N1, Nn is a certain order on the set N, it allows stochastic equations to be represented by the equation 7. Where epsilon t is the white noise vector, a t the matrix that depends on unknown parameters, and ct some known vector. Thus, The produced fluid for the well M is expressed as follows. VZMT, definition for oil fluid, and VWMT, definition for water. Where delta Rm, T, where R is equal to water or oil, is a normally distributed white noise with variance sigma 2V, R. These two equations may be represented using the equation 8. Where delta T is the vector of white noise, Bt a matrix depending on the unknown parameters eta, and dt a vector depending on the unknown parameters 11. Equations 9 and 10 define the equation of state of the Kalman filter model. From the estimates of the parameters theta and eta, the impact of injection wells on production wells is estimated. Let W, N1, N2, be the set of all paths joining vertices N1 and N2 with a minimum length. We define the value of the influence of the injection well L on the production well M, trough the response function Ym, L, where the routing of the oil and water is performed, over all edges involved in the path Y belonging to Wn1, N2. The response function is defined by the equation 11. There are no restrictions for GT. The process of implementing the model can be consulted in detail in the paper. Modeling fluid flows in oil fields using the Kalman filter. The model was applied to a field with 13 production wells, 5 injection wells, with a history of 533 months of production. Injection wells start operating after 300 months. As independent variables, the latitude and longitude coordinates of the drill points, and the bottom hole pressure are used as additional variables. If the function gt of hidden variables is known, then Vt plus 1, the production in wells can be predicted, using the equation 1. For hidden variables, a graph with a hexagonal grid of vertices is used, i.e., each vertex has 6 neighbors, and they are all equidistant from each other. The number of vertices is n equals 70. Next figure shows the production at the well with index 4, green, and one of the sources, well 9, red. The first graphic shows the production of oil and water in well 4, and the second, the production of oil and water in well 9. If the GT function is known, using this model, production in wells can be predicted. Figure shows the forecast of oil production for the year ahead, 12 months, at the well 4. The vertical dashed line shows the beginning of the forecast period, in which the actual production Vt was unknown. Figure shows that a fraction of water will flow from the injection well to a production well, and that all water flow will be distributed through the network of production wells. The image presents the flow in the reservoir in detail. The real goal of having a reservoir model is to be able to perform water injection operations, to optimize the management of the well field. The high methodology involves linking predictive and prescriptive artificial intelligence. In this case, the predictive model is based on the Kalman filter, and the optimization model is based on the linear response theory. The linear response theory is synthesized by means of the reservoir response matrix, which relates QA, the rate of injection or extraction, of gas and or water, and QB, the rate of oil extraction, with the change in pressure SI, at the selected control points. The example considers I is equal to 1, 2 or 3. The response matrix must be estimated, by conducting experiments with the simulation model, and is the link between the two models. Optimization knowledge expert systems. The current computing power makes it possible to design complex optimization processes, in which information is exchanged autonomously between models. One of these concepts is the artificial hippocampus, which corresponds to the vision of expert systems, traditional in artificial intelligence. For cases of high dimensionality, for example, oil fields with many wells, or oil field design processes with many possibilities, the production of the elements of the response matrix can be accelerated, considering the availability of CPU processors, which currently has an oil company. The basic idea is to think about to include the simulation model within the optimization model. This is a viable idea, but it involves high complexity in mathematical formulation, and high computation times. The production of the elements of the response matrix may be a standalone process, therefore, they can be generated outside the optimization process, and may be storage in an optimization knowledge database. The simulation model could be the Kalman filter model of the reservoir. Then, the elements of the response matrix will be used by the coordinated optimization model, when the optimization process requires this information. If large-scale optimization methodologies are used, it is possible to establish a dialogue between the information system and the optimization model, as the optimization process progresses, decreasing the dimensionality of mathematical problems and speeding up solution times. It should not be forgotten that the cases in the real world are complex and of high dimensionality. For example, it is quite possible that be necessary to coordinate simulation models of multiple reservoirs. Like Herbert Simon, Hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.